Welcome, Mark.
Anyhow, I just want to say welcome, everybody. Thank you for being here. And especially those of you who we haven't seen an awful lot lately. Some of you are brand new faces, or maybe some of you have been around this for a long time but haven't checked in for a while. Just great to see all the names in here. Really, really thrilling to have such a good turnout for a meeting like this one today. And I wanted to urge any of you who are brand new to leave us your contact information, your name and your email in the chat, and we'll be happy then to put you on a regular notification list. We send an email about once a week. Some of you might be on a list that gets an email about once a month, like for these. If you want to be contacted more often, do the same, put your name in the chat, and we'll put you on our more frequent, more active member email list. Well, yeah, I'm thrilled about the turnout, and I want to turn the meeting now over to Julia, who's going to introduce our guest, Julia Dederer.
Yeah, first of all, Joan, would you like to say a couple of words about what the Foundation for Climate Restoration is? Just briefly, that'd be great.
Oh, sure. Why we're established in the first place is because of a particular vision that we have, and our vision is to have our climate restored by 2050. So however you want to participate in that, you're part of what we're up to, and we're part of what you're up to. And these particular calls every second Wednesday of the month are called our Founder Series. And the purpose of the Founder Series is to present people who are particular experts in different areas of climate restoration. We love that you're on. We love that you're on the Founder Series. We'd love for you to participate with us every Wednesday in our Founder Series and our community calls. We're happy you're here.
Great, great, great. Yes, and you know how we define the climate restored is CO2 back down to 300 parts per million by 2050. And that there's all kinds of aspects of the climate restored, but that's our focus, and we're really excited to have Brent here today to talk about synthetic cement and what he's done with that. One of the things I love about what I read about him, his PhD thesis was he figured out how shellfish and corals make limestone from CO2 and calcium. And I love that. I just love that about where he started out. And I'm just going to turn it straight over to you, Brent. And after that, we'll have an opportunity to do questions and answers, and I will facilitate that. And take it away, Brent. It's all yours.
Thanks, Carol. Well, it's nice to have a chance to share some of what we're doing with everybody. And you know, if you're not familiar with what we do, we make limestone in big piles like this out of CO2 and calcium, and break it up and use it as the aggregate in concrete and store the CO2 in the concrete. Wow. I'm going to share some slides with you now, and we'll look at in more detail about what we're doing. I assume you can see those slides okay?
Yep.
Okay, great. I love to show this picture. It's where I am right now. This is an aerial photo of the plant where we've been operating in Pittsburgh, California, which is near Martinez and Antioch, for a couple of years. And we're in the process of automating it now and operating it continuously, which is a big milestone for us because it demonstrates scalability of what we're doing. But the plant has been operating for a couple of years, and it's allowed us to make a lot of mineralized CO2 aggregate and test it in concrete. And I'll show you what that's about. So what is it about limestone that makes it a great place to store a lot of CO2? Well, over 99% of all the carbon on Earth is already in limestone because it's the lowest energy, other than maybe diamond or a way to store carbon. And the fact is that over 99% of all the carbon on Earth went through the process that limestone is made at some point. And it's a process we call biomineralization, meaning almost all of limestone is the skeletal remains of marine organisms that have piled up. And it's interesting because not only is most of Earth's carbon tied up in limestone, but limestone, other than water, is the largest commodity on the planet. And there's over 50 gigatons of rock mined every year, and most of it's limestone. And limestone is calcium carbonate, and every mole of calcium carbonate contains a mole of CO2. And so if I make a ton of limestone with CO2, I'm permanently mineralizing and sequestering 440 kilograms of CO2 permanently in a product that's already the most used product on the planet anyway. That's the basic idea. I know all of us on this call probably think about how much reduction is needed a little differently than the mainstream. But no matter how you look at it, unless we can take tens of gigatons out of the system, we're really looking at a different outcome. And we all agree and understand where a lot of the new CO2 that's going into the atmosphere is coming from. So what we're doing is we're going out and we're capturing as much CO2 as reasonable and mineralizing it.
Yeah.
So this is a picture of the last 650 million years. It's called the Phanerozoic. It's the time when
I believe so. Let me check my.
Let me interrupt you for a second for two things. Would you put yourself on mute if you're not the speaker? And or
I've got
Mark
3:40.
Batchelder, can you put that person on mute? And the other thing is, you can click slideshows so that the view is bigger of your slides, Brent.
Yeah, I'll do that.
Okay, great.
Right.
Bob, can you hear us?
All right.
I'll-
So we've got somebody who hasn't been muted still. If you could find him, Mark Batchelder, and mute him, that'd be great.
Bob Wright, can you mute yourself?
I'm terribly sorry. Of course.
Okay,
Thanks.
go ahead.
So the Phanerozoic era is the last 650 million years when life's been on the planet. And there are multiple studies that have hindcast CO2 levels over the Phanerozoic time. And as you can see right now in the Neogene on the far left, CO2 levels are amongst the lowest they've been since life's been on Earth based on the data we have. And the majority of the history of life on Earth looks like CO2 has been about 5 to 10 times higher. And it's important to understand that it doesn't change our mission much, but it also gives you a little insight as to how dynamic and how precise we really need to be thinking about climate and CO2. And if we look particularly, because we're right now in this discussion, we're interested in mineralization and mineralized organisms over the same period of time, last 500 or 600 million years. There are different calcium carbonate minerals that have formed when CO2 has been high versus low. For example, 100 million years ago, during the Cretaceous, there were dinosaurs, there were no ice caps, sea level was much higher, CO2 is quite high. And but it's an interesting time because what we've learned is one of the most prolific calcifiers on the planet they're called coccolithophorids, and if you fly over the Atlantic in the summertime, you'll see wisps of white on the water that go for hundreds of kilometers. Those are blooms of these coccolithophores that are producing a type of mineral called calcite. It's a type of calcium carbonate very prolifically, and they're responsible for, a significant, I probably could say most of the carbon capture and sequestration going on in the planet right now. And there's been a lot of experiments done with them. You may have seen pictures of them. They're beautiful. They look like snowflakes, but they have a lifespan of about 12 hours. And they're pure calcium carbonate. And study after study has shown that as you increase the CO2, that's in equilibrium with the water they're living in, they calcify more and they make bigger calcium carbonate shells. And when this work was criticized, she went back and took some corings and showed that if you go back 200 years, they get smaller, when CO2 is lower. And so, a lot of our thinking about a lower CO2 world it isn't exactly what we're actually observing. In the case of these guys, if you go back to a pre-industrial atmosphere, they make smaller skeletons, which isn't necessarily bad, but they're producing actually less calcium carbonate than they do when there's more CO2. So just kind of thinking about that, it's good to ask, well, where is all the CO2 anyway? Where's the carbon on the planet? And it's almost all in the lithosphere. There's about 100 million billion tons, 100 million gigatons of carbon in Earth's lithosphere in the form of carbonate and as calcium carbonate. In the whole hydrosphere, all the oceans, lakes, rivers, ice caps, there's about 38,000 billion tons or 38,000 gigatons. In the whole terrestrial biosphere and soils, there's 2,400 billion tons or 2,400 gigatons. And in the atmosphere, there's about 800 gigatons, 800 billion tons of carbon. Now in the hydrosphere, the carbon exists as bicarbonate ion primarily. In the terrestrial biosphere and soils, it primarily exists as complex organic molecules. In the atmosphere is the one place where CO2 exists, carbon exists as CO2 itself. And all these reservoirs are all in equilibrium with each other, and they're exchanging carbon back and forth relative to their concentration. So if we look at all the different buckets where carbon exists on Earth, the one in the lower right is a much bigger number, I think you can tell, than any of the others. The numbers in the deep ocean are pretty big, but the atmosphere is pretty small. But the thing to remember is not only the absolute amount of carbon in these different places, and it's the different forms that it exists, and understanding that they're always in equilibrium. Like, the ocean surface is always in equilibrium with the atmosphere, and they're all exchanging at all times. So if we increase CO2 in the atmosphere, that has an effect on different forms of carbon, like bicarbonate ion concentrations in the oceans. If we lower the atmospheric CO2, then the oceans will outgas CO2 to come back into equilibrium. So we know we've got plenty of CO2 coming from lots of different sources. But with our particular interest in this talk we're having right now, we want to put as much CO2 into the lithosphere in the form of rock, like the White Cliffs of Dover, as we can. And we want to do it really fast. And if we go back 100 million years to the Cretaceous, when CO2 is 5 to 10 times higher. It's also when we actually sequester the most CO2 in limestone. So the Austin Chalk and the White Cliffs of Dover are both about 100 million years old. And it was during that high CO2 episode when all this limestone was formed. And that gives us a lot of important clues about, you know, what's really going to allow us to mineralize the amount of CO2 we want to mineralize. And I just want to remind everybody, you know, for example, this is a picture of a cartoon of a coral. There's a picture of a coral, and then there's a picture of coral that's, you know, a few tens of years old in the sediment that's on its way to turn to limestone. The whole idea of using those materials and those different minerals that are formed in different processes, which are quite complex, but they all involve capturing CO2 and mineralizing it, has been around for a while. This is during the Second World War, there was a group called the Seabees that would go out and build these airfields on low islands or atolls. And what they do is at low tide, they would go out with bulldozers and get all the sand, which is 100% composed of the skeletons, broken parts, sands of, you know, echinoderms and corals and mollusks and green algae, and put it on up on the land, and then irrigate it with fresh water. And when you do that, it recrystallizes and forms hard limestone.
Wow.
And those runways are still there. And I, you know, during my dissertation work, I used to fly an otter around and land on all these runways on the different islands. And they're great. You know, limestone is a great fundamental building material. And if you can control it, I mean, go to a country like Italy, everything's built out of limestone, right? The pyramids are built out of limestone. So it's a very, very common building material. I love this slide because while he was still alive, I used to go visit George Shultz all the time over on campus. And I was showing him this picture, and he said, "My God, I can't believe it. I was there. I was there as a 19-year-old Marine. And I observed all these operations with the sea beats." And the reason that was so interesting is George, aside from his civic duties, you know, of Secretary of State and Secretary of Commerce, had also been the CEO of Bechtel, you know, which is a big construction company that builds, you know, airports and things like that. So he really loved this photo. But the whole idea is we've got this abundant building material that's usable and can be incorporated in a built environment. And it's a huge opportunity for carbon mitigation. Okay. There we go. It turns out the actual minerals that form limestone are under intense scrutiny now. They're called amorphous calcium carbonate, and they form these little spheres that are become terminally differentiated to form specific minerals. And the trick of how corals do it and how mollusks do it and how we're doing it is related to being able to control these little spheres, which are, you know, less than a few microns across, and in a way that we can direct them to form materials like we're doing over very short periods of time, like over minutes.
Wow.
So let me just kind of review what we do. I know a lot of you already know this, but on the left side is what Blue Planet does. We encounter CO2, and in one step, we convert it to calcium carbonate, which hardens into a mineral.
You're no longer sharing your screen?
No, I didn't know that. It stopped moving.
Yeah. Reshare. Oh, good.
Can you see that?
Not yet.
Okay.
As I might say, almost.
Yeah. Wonder what happened. Oh.
Maybe stop sharing and start sharing again.
Yeah, no, I'd like to. I'm having to get back to the basic. Okay, here we go.
There
How's
we
that?
go. Yeah, and now make it full.
Yeah, it's something about making it full that freezes the screen, but
Oh, now we're good. Yeah.
yeah. So on the left is the idea of what Blue Planet does. It's the when we encounter CO2, we convert it directly in one step, which takes a few minutes, to a calcium carbonate that hardens into limestone.
Wow.
What most of the world's doing today that's trying to mitigate large amounts of CO2 is capturing CO2, purifying it, which usually is quite intensive, but energy intensive. When it's pure, you can liquefy it and pump it around and push it in oil fields and get more oil out and things like that. So there's a ridiculous diversity of approaches and funding doing that to inject it into the ground. And that general mechanism only exists when there's a subsidy of some sort, because there's no product of any kind that comes out of that, except maybe being able to yield more oil out of an oil field. By contrast, with Blue Planet, we don't calculate any kind of government subsidy or anything, even or a voluntary credit for the CO2. The economics of making limestone, which again is the largest commodity on the planet, all the infrastructure is in place already to move it around, you know, funds the whole process. The plan I'll show you was funded with debt because it, you know, it has a great investment profile.
Can I ask a question?
Sure.
Yeah, so your source for CO2 is from fossil fuel emitting sources, right? Like,
Yeah,
that's
our chemistry has no preference for where the CO2, it's just the CO2
can you do
molecule.
can you do atmospheric CO2?
Yeah, there's absolutely no difference between atmospheric CO2 and CO2 that comes out of a.
No, but can you do that? Can your process do that?
We do it all the time.
Okay, so like you can
yeah.
do direct air capture then and go into limestone?
Yeah, we do that all the time. It's just highly inefficient, and there's no direct air capture process known that doesn't produce more CO2 than it actually absorbs. But yeah, we do that.
So you're saying like Climeworks and what was 1.5 and all those places, that what they're doing is absolutely useless?
That's correct. But we're not, I mean, look, we're giving them a chance. So they all come to us with their CO2 because they don't have anything else to do with it. And we
what about
mineralize
Heirloom? Heirloom uses limestone. Direct, but I'm just saying that because I
no,
know
that's not true, by the way.
Really interested
Heirloom
in
doesn't use limestone. Heirloom calcines limestone with renewable energy and turns it to calcium oxide and then tries to get it absorbed.
Okay, so but what you're showing here is like a power plant, right? That you're getting the CO2 from, correct? Like in your image there on the left with the little smoke coming out.
Yeah, if I had my smartboard at Stanford, I could draw cartoons of a lot of things that produce CO2.
Right. So you're saying you could put you can take CO2 from anywhere.
Yeah, there's no difference between CO2 from any of the sources. What's different about them, and I'll show you a slide about it in a second, is that it tends to come in different.
Edith, wait a minute. A good question, Edith. Really good question. And can we hold them until he completes? How many more minutes till you complete, Brent? Because there's some good questions I know out here.
Yeah, well, let me answer them with my slides, and then if they're still there,
Yeah, exactly.
we can
Thanks.
address them.
Perfect.
So this will help a little. So understanding the basic process, you know, it can be flue gas from an industrial source. It can be direct air capture. It can be really a whole variety of CO2 sources, but they're put into a large column, and the CO2 is just like it diffuses in the ocean. It's absorbed in the same way, and we precipitate calcium carbonate of those amorphous calcium carbonate types that I showed and turn it into limestone. And then the capture solution itself is recycled. It's interacted with waste materials like waste concrete, and then it goes back through the whole system again. The products that come out are different types of limestone, like coarse aggregate or sand, and then the material from which we leached and renew the calcium and you know, had left over, also reused. So it provides another source of rock, which I'll explain later. But there's a shortage of aggregate around. We take the limestone and we use it to make concrete. Concrete's about 80% sand and gravel, and most of that is, the most common type is limestone. And we make these different limestones. They're tested, and what's shown here in the graph on the right is the dark blue on the left is one with no calcium carbonate, you know, aggregate in it. The gray one is about 30% calcium carbonate. The light blue one is about 50% calcium carbonate, and the dark blue one is 100% calcium carbonate aggregate in it. And that's it, 3 days, 1 week, and 4 weeks. What got me originally into doing this was I'd already developed a cement in the late 80s that was used in and is still used in orthopedic surgery. On the right is just a publication I had in Science in 1995, where we reported our first years of clinical experience. On the left is an article from the Journal of Bone and Joint Surgery, and of 200 peer-reviewed medical articles on the cement that we developed. And this whole process helped me kind of think about and understand how to commercialize something in a tough market. Getting new things into orthopedic surgery isn't really an easy thing to do. And so that's, you know, sort of an insight about all the work on cement and concrete right now. There's a whole variety of approaches being taken, and most of them are just to lower the impact of cement and concrete on the environment. And you know, Blue Planet would be in number A, where we're making aggregate, but B and C are examples of cement replacements, where people are trying to replace the cement itself. And D is an example of where someone buys that refined, purified CO2 and sort of perfumes plastic concrete with it to get some of it to absorb. If you look at the actual impact, this is a graph put together by an analyst using a rating called Carbon Star, which is sort of patterned after Energy Star, but it looks at how much carbon is actually trapped and sequestered in the material. And you can see ordinary concrete on the far left has a carbon footprint of about 385 kilograms per cubic meter. And as you go through all these different approaches, they're all still have pretty large carbon footprints. But it's when you get into these groups on the right, like Blue Planet, that are working on the aggregate itself, where you make these huge differentiators in terms of sequestering a lot of CO2 in the concrete. So you're not just making it less bad, you're actually making it carbon negative. So you're net sequestering a lot of CO2. Here, this is to answer your question, Edith. So what you see along this chart is on the left is CO2 emissions in megatons per year in these different areas. And you see on the right is cost to capture CO2. And along the x-axis is the concentration of CO2 in the different sources. So on the far right are natural gas power plants and furnaces and small boilers. And they contain, 4 to 10% CO2 in their exhaust. And so to put direct air capture in context, the atmosphere is 0.04%. So if you look at, say, coal-fired power plants and oil and diesel plants, they're 10 to 15%. Cement plants are 20 to 40%. Ethanol fermenters, refineries are more like 100%. What you can see is the cost, and it turns out the amount of energy necessary to capture that CO2 is inversely proportional to the concentration. So for example, if you want to get 1 ton of CO2 from direct air capture, you need to process 1.25 million cubic meters of air, so that's sort of the equivalent of the Houston Astrodome. So if you can move the amount of air in the Houston Astrodome and process it all and get a ton of CO2, I'll take it. We'll put it in our process, we'd be happy to. But, the scientific community understands that's thermodynamically going to be a real challenge.
Which vertical axis is your green line?
The one on the left. Okay. A little bit more. So let's talk about the CO2 itself and how to manage it. What's shown here is the volume of 1 ton of CO2 in various forms. So aragonite is mother of pearl, it's calcium carbonate, and 1 cubic meter of aragonite holds about 1 ton of CO2. If you liquefy CO2, you can get 1 ton into about 1.1 meters cubed. If you look at Blue Planet's aggregate, it's about 1.6 cubic meters for a ton of CO2 because it's porous. If you look at the solution that forms when CO2 interfaces with aqueous solutions like seawater, for example, it's about 11 cubic meters for 1 ton of CO2. If you have pure CO2 gas, it's about 35 cubic meters. If it's the flue gas, like you take from a natural gas fired power plant, it's 80 cubic meters. And if it's just air, it's about 1.25 million cubic meters to get 1 ton of CO2. So that has implications in terms of what the most practical modality is for managing large amounts of CO2. And right now, if you go out and see what people are doing, 99% of everybody, the direct air capture people, the refineries, the entire oil industry, they're liquefying their CO2 so they can put it in pipelines and inject it underground. And that's not how limestone is formed. Limestone's formed from marine organisms, which are getting calcium and bicarbonate out of the seawater. And it's just an approach that's not being used right now. And what that allows you to do is think about managing large amounts of carbon in a completely different way. What's depicted here in this upper area where it shows CCS, that stands for carbon capture and sequestration, which is what most carbon capture work is using now. It goes through a purification and compression step to go into pipelines, to go to subsurface storage locations. What we're doing at the plant, it goes through an absorber just like the ocean. It makes bicarbonate ion, which is like a liquid. There's no compression. It can be moved like water in old water pipes out to the process. And what that does is it means we consume about 1/40th the amount of energy moving the same amount of carbon the same distance. And it opens up the possibility to have these networks at ports where we have hubs that allow us to move a lot of CO2 in a really low energy, low capital cost fashion and sequester it into the building materials and transport it. So we're looking at hubs all over the world in the form of ports that a lot of ports they're called pre-Panama Canal ports that are all over the place that are underutilized and are really well set up. So without building a whole new infrastructure to support this, this whole idea can be transposed into sort of regular infrastructures. So for example, this is a port we're looking at in France right now. And the red is solid materials that can move on barges. The blue lines are this solution that we form when we capture the CO2 is a bicarbonate solution. And the yellow areas are gas sources like refineries and things like that. And we really believe this is how it's going to roll out is large engineered projects at ports where you can move a lot of mass of rock and limestone, where there's CO2 available, there's transport of finished goods. And the product itself is carbon negative, which offers a whole new dimension for people thinking about how to reduce the embodied energy in the built environment. They can actually make buildings that are carbon negative. And there's almost 5,000 power plants in the world that, seem to still be operating. There's over 1,000 cement plants in the world where we can capture the CO2, pretty high concentrations. So let me tell you exactly what we're doing. And then I'll make sure we have time for questions. We started pouring concrete up at SFO in Terminal 1 a few years ago. And
Right.
The concrete we're forming, according to the Carbon Star rating that the airport specified, was about almost 500 pounds carbon negative per yard. So this is a list of the ingredients that go into concrete: cement, water, and coarse aggregate and sand, fine aggregate. And sometimes there's an admixture as well. And you use a lot of electricity processing, making concrete as well, mixing it, and water. So if you go through and you use all the cement you would normally use, so that's about 600 pounds of cement, all the water you'd normally use, all the electricity you'd normally use, but the sand and the gravel comes from Blue Planet, you end up with an overall carbon footprint of negative 500 pounds. So if you're an architect and you're planning a building that's going to have 100,000 yards of concrete, instead of 100,000 times what would normally be about a carbon footprint of 600 pounds, it's actually times negative 500 pounds instead. So you can really sequester a lot of CO2 this way. And it's a way for, say, the city and county of San Francisco, who has carbon objectives, by building more stuff at the airport this way, they'll actually be able to meet their carbon objectives by doing the same projects they were going to do anyway, just using a carbon negative concrete and using their procurement power to sequester CO2. We're going through upgrades at our plant here in San Francisco right now, like I mentioned, to be continuous and automated. But this, for example, is how a government can use their procurement power to mitigate CO2 without spending any more money than they would have spent. This was the spec for the cast in place concrete in Terminal 1. And they specified our lightweight aggregate for all the, the ramps and all that kind of thing. So moving on a little, the product itself that we're making from CO2 is used all over the world, anywhere where they're making concrete. China is doing most of it right now. But if you go in the lower left here and just look at California, the green bars are the projected need for aggregate in these different counties in California. And the orange bars are their permitted supply from quarries. And in all these cases, all over California, we're going to be running out of aggregate. We already are, and we're importing a lot of it from British Columbia and other places and barges, which has a huge carbon footprint associated with it. So it's a, worldwide, there's, a huge potential. If you look at some of the projects here in California, the 49ers Stadium used about 80,000 tons of concrete, and the Salesforce Tower, it just shows the Hoover Dam for comparison here. And the high-speed rail will be one of the largest CO2 emitting things the state's ever done.
My God.
If you look at the Bay Area Air Quality District, a lot of people don't know this, but they were the first air quality district. They were formed in the 50s, and they were actually regulating CO2 in the 50s. And then the Clean Air Act came along, and it became a federal thing. But anyway, they've set objectives, and just like every other group that set objectives, we're nowhere near where we thought we would need to be. So there's a clear local desire to do that. And you can go to any venue like the Bay Area and see how much concrete is placed annually, and look at the market. And even Saudi Arabia is importing sand. And so the type of sand they have in Saudi Arabia is windblown, and that's not what you use in concrete. You use water moved sand. So looking specifically at the Bay Area, in the North Bay, there's about 110 million tons of permitted reserve. The 50-year demand's about 500. South San Francisco, same sort of thing. The triangles show where concrete is ready mix. So there's a clear distribution pathway for all the rock that's going to be produced. Our plant's on the water, so we can move long distances fairly inexpensively. These are some of the prominent ready mix plants. These are the concrete trucks you see driving around that are actually delivering concrete. Okay, so just to kind of make it so we can get to questions here, we're projecting right now that potentially we could be capturing 200 million tons of CO2 by 2030 with our current plans. That translates to about 500 million tons of rock. And there's a whole bunch of stuff going on relative to concrete, but nothing has the same impact that Blue Planet has because we're making aggregate that goes into the rock. Where we are right now is the plant that we're automating is scaling up to tens of thousands of tons of CO2. And we have another commercial side at a biorefinery that we're developing another plant up in that same area. But to put it in perspective, if you look at what's going on with carbon capture and storage right now, which if you talk to anyone in Washington, they'll tell you that's the main way we're going to address CO2. Right now, that bottom axis is capture capacity in megatons. You can see it's a total of about, if you look at the blue line, advanced development, that means they're about to get their permit. If you added them all up, it'd be about 100 million tons worldwide, all inclusive. But actually, the pink one is what's in construction, and it's the light blue gray one that's operational. So there's about 40 million tons per year capability globally right now. That's what we're doing. And there's literally billions of dollars being invested to get this 40 million tons a year. So one concept that's been really difficult to get across to people are the difference between megatons and gigatons. And I finally found a way to communicate it to people, because they can think about megabytes and gigabytes on their computer. And there's 1,000 megatons in a gigaton. And 1 gigaton's 1 billion tons. And 1 billion tons is 100 million tons. So if you look at all the anthropogenic CO2 emissions being captured today, it's about 40 megatons. So it's a pretty small number. So how are we possibly going to get to a gigaton? And we've put together financial models for our plant with about 2,500, 400,000 ton plants. By 2050, you could get to a gigaton, and that could be done just by one sector alone. Like the cement industry could easily do that. But there's not just the cement industry, there's refineries that are putting out pure CO2, which is the easiest to capture and mineralize. They're still building coal plants. I wish they weren't, but they are. And there's also waste energy plants that we're working with. We're working with steel plants, anywhere where there's a significant amount of CO2 coming into the system. So this is our math on how we get to a gigaton. And just to finish off, the way we're implementing it is we're forming partnerships with large engineering firms all around the world right now who want to take carbon mineralization to their clients, and their clients are asking for it. And we've created something we call Blue Planet University, and it's an online program. Some of you know, one of my management team members is the founder of the U.S. Green Building Council and invented the LEED scoring system. And what a lot of people don't know about him is he's also developed some really successful online universities before. And we found it's about a 4-hour program. We can take a technical individual, trained engineer from any engineering firm and get them up to speed really quickly with this online education. But we have a lot of other things we're doing. We're advocating for mineralization, which currently isn't considered by the California Resources Board as a form of carbon sequestration because they don't know about it. So there's a big need for education. They only acknowledge what the oil companies do, which is inject CO2 into the ground to get more CO2 out, more oil out, as a legitimate form of carbon sequestration, even though the CO2 comes out when the oil comes back out.
Right.
So this is how we aim to do it, and that, in probably a most conservative way, gets us out to 2050. If you add more industries on, more sources of CO2. It could even be more aggressive than that. So that's why we're working on sand and rock. We think there's a real viable path to get there. But thank you for allowing me to present to you, and I'm happy to answer any questions anybody has.
Well, thank you very much. I want to say one thing before I call in anyone. Personally, I know a lot of this was above my pay grade, and some of you may feel the same. And he had to go very quickly to get us through the whole thing. And, you have such a calm way of presenting, and yet it's the strangest experience of having been in front of a fire hose for 45, 50 minutes, even though you have such a beautiful, calm way of presenting. So I know the questions could go on for an hour. I am going to extend the call for those who wish to stay on for 15 minutes. So, but please be, cognizant that everybody's probably got a question that could take Brent an hour to answer. So we're going to see how many questions we can get up there. Sean, you're first to model that for us.
Oh, good luck with me then. I have three, could be short questions, but the first one should be a simple one. I don't understand. I didn't quite capture. Where do you get the calcium from? The second question is on legislation and lobbyists. What the heck why aren't we getting more lobbyists out there? Why isn't the government mandating, not just the California government, but national, federal, across various countries, my country, Canada, why aren't we legislating that? Or what can we do to do that? And how do we invest in your company? Those are the three questions that I have. So I was trying to figure out how to invest in Blue Planet systems, and I can't figure that out.
Well done. You modeled that beautifully. Go ahead, Brent.
So at the plant in San Francisco, the calcium source is returned and demolished concrete. So there are people called concrete recyclers that take all the demolished concrete and they break it up and they separate what was the cement from the sand and the gravel, and they wash it and sort it and clean it. And there's a part of it they don't want, which is the part that was the old cement, which is the part we do want. And so we have relationships with them. And legislatively, I think it's sort of a revolving door between the energy industry and the Department of Energy. And it's sort of like if you're a hammer, everything looks like a nail. And it's hard to, the thought is, why would you want to do anything else than inject CO2 underground and get a subsidy? Yeah. I mean, whole programs are designed around businesses that are dependent on a subsidy. And I've learned from personal experience that building a business on a subsidy is a really risky way to go. And I'll defer the investment question to maybe an email.
Great. Okay, good. Alan?
Yeah, he's a retiree from Lawrence Livermore and adjunct professor at Stanford, formerly physical chemist, geochemistry through material science. I really appreciated your presentation. I have a gazillion questions, but mostly I would like to ask about the study from Lawrence Livermore that says that a primary way of making California carbon negative is to gasify waste biomass, agricultural, forest, all that sort of stuff, and then sequester the CO2 in depleted reservoirs. And by the way, it's not to get more oil, it's to actually just leave it there. Have you made any contacts with the Lawrence Livermore people? Because it seems to me like making calcium carbonate would be a as good or better way of getting of taking that CO2 from the gasification process.
Yeah, no, thanks for the question. I just returned from 3 days at Fawn Leaf Lake with half the audience was from Lawrence Livermore Lab, work on a crystallization society. But in fact, up at Pittsburgh, California, we're doing program now with what's going to be a biodiesel refinery. In their case, they're actually starting off with cooking oil. There's a lot of it. And I think a lot of people would agree with you that that's a great way to pull out some CO2. But it's great if you have something good to do with it too, instead of, if you can, turn it into a product that's useful.
Okay.
But thank you very much for the question.
I mean, Roger Ains is a good friend of mine. I don't know if he was there, but we go back 40 years.
Well, there you go. Roger's been working on this idea for a while.
Great. Okay, David?
It seems that the perfect location for a future business would be a place where there's a lot of used concrete and a continuing source of pollution. That is the source for your CO2 coming out. And should we be not working on the reduction of those coal plants or cement plants? And the balance is a little hard. That's too complicated a question to get to quickly. I just wanted to also say that a potential answer to your what about policy approach is Citizens Climate Lobby, which I just came back from the annual conference. We had 1,000 people. We had 442 meetings on Capitol Hill, including 97% of the senators' offices. And each one of those meetings with 5 to 8 people are peaceful and respectful, and they listen. And we already have a greenhouse gas reduction action team, a great team, and a subgroup of that called Blockheads, which is working on concrete projects in Wisconsin and Colorado and Illinois and New Jersey and elsewhere with different technologies. So I think there is an alignment with a functional lobby and policy lobby approach. If you're willing, we're willing, I believe.
Yeah, thank you very much. My vice president of government affairs is based here in California, and we are putting a lot of our efforts actually in California. And we have a firm in Sacramento that's the guy's Mary Nichols, former assistant and PhD out of Davis, and wrote a lot of California legislation right now. But I've testified before a subcommittee of the House on this. I've testified before the subcommittee of the U.S. Senate. I've gone to all the COP meetings and since Copenhagen, in 2009. So I've been very involved, and we really appreciate the efforts of the Citizens Climate Lobby as well. We're sort of more specialized, and we have some specialized collections of like companies that are working together, but I know everyone is all working toward the same thing and trying to move forward.
And do you have standards? Do you have standards agencies supportive of your chemistry?
Yeah, if you looked at the Carbon Star rating system, that was developed by the Canadian Standards Institute, and it sort of separates the wheat from the chaff. It requires a quantitative measure of the amount of carbon sequestered, and provides methodologies, to verify that. There's a lot going on right now especially in the voluntary carbon credit market and the sales of credits. It's a real wild west out there right now.
Thank you.
Yeah, thank you for your comment.
Yeah, Paul? Yeah, unmute. Unmute, Paul.
Thank you, Brett, for being here. We all appreciate it. I have a simple question. We are in the business of climate restoration, and I think that means extracting carbon dioxide and doing something with it, putting it away. So my understanding is that in your business, you take carbon dioxide, for which you have many sources, and you're transforming it into concrete. And in that process, you are eliminating carbon dioxide from the atmosphere, which is what we all want to do. Is that about approximately correct?
Perfect. A plus.
Wow. Thank you.
Edith.
Yes, hi. Well, first of all, I think it's, I am in the built world professions. I'm a landscape architect and urbanist, and so I work in cities and I work in cities all over the world. And I think this is an incredibly exciting project, the way that you guys have mapped it out. It makes a lot of sense. And so if we wanted to ever want to use your negative concrete, we would need to coordinate with you your facilities, which are still just starting to spread out. Is that right?
Yeah, that's right.
West
Generally,
Coast, yeah, the West Coast, if you're in the San Francisco area, you're in good hands there. But like, let's say you have a project in on the East, on the East Coast, or somewhere in England or whatever.
yeah, generally you don't ship concrete more than about 50 miles, and the usually less than that. But if you saw my rollout plans, we have projects going we have a huge project going in Singapore right now. They're concerned about sea level change and sea walls and things like that. We have a big project in Washington State.
Okay, so we would have to check
you know,
back. We would check back with you and see what possibility of the potential.
Yeah,
okay. So the second question I have, which actually relates to what the person just said before me, is that, I mean, in addition to taking CO2 that's being currently emitted or will future be emitted into the atmosphere, in order to restore the climate, it's my understanding that there's legacy CO2 that has to be taken out of the atmosphere that's already been put up there in order to get the parts per million back down. And that's part of the IPCC acknowledges that in conjunction with the reduction of emissions. So I think there's a two-part process here where the direct air capture has to come in, even though it seems so incredibly inefficient the way your graphs and technical specifications showed. It has to happen, doesn't it?
Well, with
go ahead.
Any process, the first question you ask, does it emit more CO2 than it actually captures? And there are very few processes that claim to be carbon sequestration that emit less CO2 than they actually capture. And processes like purifying CO2, for example, are extraordinarily energy intensive. And so the way they address it is they say, well, we're just going to use renewable energy. Well, if you pull renewable energy off the grid to capture CO2, someone's burning coal somewhere else to put it on the grid, So it's sort of there's a lot of that out there, and those people are selling voluntary credits to Microsoft for the CO2 they're capturing. And, like I said, it's the wild, wild west.
Right, but that doesn't really. My question is, theoretically, there is legacy CO2 in the atmosphere that has to be removed, and and innovations are happening to make that process more feasible, more realistic, less expensive right now. But isn't it true that that has to happen? That the legacy CO2 has to be moved, and that would have to be through some kind of direct air capture or planting forests or the atmospheric CO2 down.
Doing that without addressing the primary problem of where most of the CO2 is coming from, would be fruitless, right? I mean, coal plants alone are putting out 11 billion tons of CO2.
Not either or. They both have to happen, but you don't agree with that?
I think there's if you look at the history of CO2 on the planet and what's been put in over time, it's certainly laudable. The problem is it's like a new shiny object. There's a lot of attention going toward something that might be beneficial after we solve the fundamental problem. But you have to think about it a lot more like a bathtub. There's say your bathtub's overflowing and you've got a faucet pouring into it and it's overflowing.
The bathtub, yeah.
It's one thing to have a qualitative understanding of what's going on there, but when you actually look at the numbers, if you remember, there are about 800 gigatons of carbon in Earth's atmosphere, and we're actively putting about 40 gigatons of CO2 into the atmosphere every year.
I know. Those are the emission. Okay, so I can't get you to actually look at the fact that there's a legacy CO2 problem. You're not interested in that, and you're not looking at that. Okay, I get it.
Well, there's certain laws you can't break, and one is the, thermodynamics, and pulling CO2 out of a cubic, 1.25 million cubic meters of air. If that can be done without actually using more energy and creating more CO2, then I'd be more optimistic about it.
Well, I think that the innovations are going to happen, quite honestly, and even with A4, and so you wouldn't even admit that afforestation and trees are useful either. The only thing you're interested in is capturing source emissions.
Now, don't back me into a corner. I'm way ahead on all that stuff. They should be doing ocean sequestration rather than air, but I'm just saying right now, if you look at the stimulus, the IRA money, there's a disproportionate amount of IRA money going toward direct air capture. And it's because a lot of the senators and congressmen don't know the difference between a million and a billion. And they're buying this new shiny object, but they're forgetting, they're letting the oil lobby handle everything else. And it's all backward right now. So we're gonna do a lot of stuff like what Climeworks does and get nowhere. And all that money could have just been burned. All the IRA money that's going toward direct air capture.
Okay, well, I'm going to call on Peter Fikowski, who can probably put the two things together for us. And go ahead, Peter.
Yeah. So Brent, you last year when the power plant next to your plant was down for maintenance, you gave me a call and said, "Hey, Peter, we had been using CO2 from the natural gas power plant, but since the plant is down, we're just running CO2 from the air and getting the same rock that we had." And so I think that's the answer that several people were looking for is when the easy to use emissions from power plants are used up. Either the power plants are converted to solar or they're already being used, then yes, the CO2 can be captured from the air. There's a question of how much more will it cost because you have to handle 100 times more air. And I thought the
4% to 0.04%.
Compared to the exhaust, the exhaust is 40%, right? No, the exhaust
4%.
Yeah. So anyway, so it's either 100 or 1,000. It's been a long time since I did the calculation now, but in any case, the point is there is material science that can be used when the time is needed to get the surface area needed. We just talked about the carbon nanotube material, but now's not the time to pursue that because there's plenty of exhaust available. But in any case, I thought that experience was useful, might be useful for people, that the process works fine whether the CO2 is coming from the air or from exhaust. And but there's plenty of exhaust to use So using it from the air is not necessary to worry about for a while. But the question I have is, we've discussed over the years that the most of, and you mentioned it a minute ago, that the most efficient way to get CO2 out of the air is with ocean fertilization. That's what nature does before ice ages. The question is, and it looks like ocean fertilization can scale very rapidly, just based on what nature's done and what we saw in 1992 after the Mount Pinatubo eruption. If for some reason we don't do ocean fertilization, how quickly could the blue planet get scaled up? So you showed the graph of 25% per year, which is just a standard growth curve. If we decided that it was important and that we couldn't do the much lower cost ocean fertilization, what's the limiting factor to scale up the blue planet system?
It's really just establishing these relationships with the engineering firms around the world, like we're doing. You know, these are, most of these plants are, requiring significant project financing and, years to build. And so that's a process that is pretty involved and involves, teams going out and evaluating locations and bringing these people up to speed and online.
So how many $1 billion are, so if I pull your slide back up here, you had 2,000 plants in 2050, I think. And each plant is going to cost roughly how many billion or million?
I don't have the financials in front of me, but a 400,000 ton a year plant could cost, $400 to $500 million.
Right. Okay. So, so 1 megaton would be about $1 billion. Right. Okay. And so we would need a total of about 2 trillion, just multiplying the numbers out.
Well, that assumes you have a good source of carbon dioxide. If you were, say, trying to pull it out of the air, you could, those numbers would be much, much larger. Because you need much more, you're moving much more air and you need much more capital equipment.
Right. Okay.
So those apply to, a refinery, a cement plant, somewhere where you're getting a more concentrated source of CO2.
So it would be doable, but 1,000 times more expensive than using the ocean fertilization. Something like that.
Yeah, I don't know the numbers for ocean fertilization, but I think that sort of makes sense.
Yeah, but I think it's important to have a plan B. I'm a big fan of doing what nature's done, which of course is also synthetic limestone. But I guess nature doesn't have big fans to blow the gas through.
Yeah, what I've said the whole time is I think direct ocean capture is probably one of the most interesting areas to pursue. But again, as I've always said, ocean fertilization for limiting nutrients is also a really smart idea.
Yeah. Great. Okay, good. Thanks. Thanks for being with us.
Yeah, thank you so much. And I'm going to end the questions now. Brent, if people have further questions, how can they reach out to you, or what resource might you have online for them to ask their questions?
Yeah, if it's not on our website, there's a website you can submit questions to, and we answer them. We have a whole team of really bright interns every summer that answer all the questions that come in.
Wow. That is fantastic, really fantastic. Thank you really so much for this. This is very exciting and a very thorough presentation. I just wanted to let everybody know that next month we are going to be hearing from, let me see. Inger, there you are. I know you're here today. And Inger Matt-Stensler, Mark, is.
Well, we could let her tell us exactly how she pronounces her name, but Inger Matt-Stensler, I
That's
believe.
great. We've had a big interest in youth action for climate restoration. And she has been working globally with activating youth. So she'll be speaking with us, and it's always the second Tuesday of the month, right? And we'll be sending out information about that. Climate restoration and global youth movement for our next.
Second
Yes.
Wednesday.
What?
Second Wednesday.
Second Wednesday. Thank you very much. And if you'd like to hear Peter Fikowski talk, we will be presenting, if we could get that in the chat, you can register. It's Saturday from 10 to 11:30. He's going to be talking about the roadmap of climate restoration, coupled with who do we need to transform ourselves to be to have it happen and to ensure the flourishing of humanity for not only generations to come, but for millennia to come. So we'd love to have you there to interact then. And there's Inger. You want to say one or two sentences just so people can know that you'll be speaking next month?
Yes, hi to all of you. I'm in Norway, and thank you for this presentation. I'm the co-founder of the World Climate School, and I know Peter Fikowski since I met him in Glasgow, and as some of you know. And I've been working on the European Youth Project, but it's extended throughout to Africa with over 30 universities. And I recently been in India, working there, and also in Pakistan, and I'm also open up the World Climate School in the United States. So I think this is so amazing, the blue system thinking, and it's a missing piece for humanity to really understand that there is a hope for the blue planet. So I'm really hoping that we can bring forward a narrative that can activate youth. So I'm happy to be here. I feel very humbled, and it's a big challenge we have in front of us. So I'm happy to be here and to contribute and to be here for the next.
And we're so excited that,
yes.
you know, how to engage the youth in climate restoration.
Yes, we'll do. You know, Ingrid, like Ingrid, you know this word very well because it's the same as the king, ing. It's the sound of the ing, and it's an old Nordic word. So ing, doing, being, acting, all the ing is getting ideas into movement. So
good.
that's my
Thank you for bringing it to us next month.
Yes, we have to go that move things forward.
Yeah, for extending the time. And Brent, thank you so much for being with us today.
Yes.
Extraordinary.
Bye,
everyone.